Welcome back. In this lesson, we're going to look at the explosions of volcanoes, which would be very, very exciting, except that it would be, I wouldn't want to get too close. So, is the volcano, when it erupts, going to be very explosive and blow its top and explode towns next to it? Is it going to ooze and be something that could be a tourist attraction that you could sell tickets for without killing people? What is it that causes these things to explode violently or gently? So we'll look at some of the details. So some volcanoes are runny, and the magma that is in those volcanoes are runny, and so they ooze out with not a lot of explosion. Some are very thick and clog up the vents and are more explosive. So we're going to talk in this section on eruptions. We have to look at the magma that is coming out of the volcano, because the eruption, whether eruption is gentle or explosive, has to do with what's coming out. So whether it is lumpy or runny, a lot of it has to do with the composition of the rocks. And if you remember, the more silica that is in a rock, the harder that rock is going to be. Well, the melted rock, the more silica that's in that rock, is going to be thicker or more viscous than if it is, say, low silica would be runny, and high silica would be very thick, viscous. Okay. Now, it takes a lot of temperature to melt a rock at sea level. So in the air, if you were going to simply melt a rock, you have a rock and you wanted to turn it into a liquid rock, it might take 1,000 degrees, 800 degrees, 1,200 degrees. It really depends. As you get deeper in the earth, something very interesting happens. The temperature at which a rock melts goes higher and higher and higher. So what at sea level might take 1,000 degrees to melt a rock, deep below the earth that's under high pressure. Remember, all these rocks, the whole ground is pushing underground. There's high pressure. As the pressure goes up, the temperature also goes up. It takes more heat in order to melt rocks. Otherwise, everywhere in the world, 2 or 3 feet below the ground, you'd start having melted rocks, and that doesn't work. That the whole world would be squishy, and that would be bad. So you'll see that as it goes farther down, it takes higher temperatures to melt a rock. And so not everywhere underground is going to be melted. You can have deep rocks that are still solid. It really just depends on where you are talking about. How close to the mantle are you? How thin the crust is in that area, etc. So we talked about the composition of silicates. Remember, more silica is thicker. The other thing that will determine on whether or not a volcano will simply ooze and run or explode is how much gas is with it. So if in that material, the melted rock, you've got water, well, water turns into a gas and you'll have a bomb. Or if there's other gases, so carbon dioxide gas, sulfur gases, other types of gases can help a volcano be more explosive, because those gases want out very, very fast. They're not going to wait their turn. They want, if there's not a vent for them to come out, they'll make a vent as they explode that mountain, the whole top of that mountain's head off. Okay. Also, depending upon what is in the rocks, some rocks will melt easier than other rocks. Okay, so the composition, we already talked about silicates, but other minerals will have different melting rates. Now, the composition of that stuff will either be thick or thin. So this is kind of cool. So water, if you have a viscosity log, this is simply a logarithmic scale of how thick something is. So if water is very thin, olive oil is a little thicker. It's more thick than water. Ketchup is thicker than olive oil. Now you start having basalt, which is like the ocean floor rock. It is runny. It's just a little bit more runny than ketchup. So it would ooze real nice. Then you have andesite. There's tar here. You also have another, there's actually another in between andesite and rhyolite, another group. Well, I've only taught you really the three, basalt, andesite, and rhyolite is the thicker in terms of silicates. There's actually a third one before you get to rhyolite. But all this is viscosity, how thick it is. The runnier it is, the thinner it is, the more it will ooze. The thicker it is, the more it will likely be to blow its top. Okay. So dacite here, you can see, is 63 to 68% silica. That's that fourth group. So basalt is low silica, rhyolite is high silica. All right, so just reviewing quickly, basaltic is that rock in the upper mantle. It's the crust of the ocean, and it has very low silica and melts oozy and runny. And so the volcanoes that are using this kind of magma, or melting this type of magma, or emitting this type of magma, are going to be nice and oozy, very little explosions. Andesitic is thicker. Okay, it's a thicker magma than basalt, and it's got about half silica content, and it has an intermediate, kind of halfway house of that. So there can be a little more, this is more likely to clog a vent, and of course if it's clogged, you'll get an explosion because all that pressure builds up and eventually could be more explosive. Okay, rhyolitic has the highest silica content, and so it's more likely to have gases trapped in it, and not just that, but it's thicker, so it's more likely to clog the vents, and so you could have more of what typical kind of, Jurassic Park kind of exploding the volcano at the top. Okay, so you can kind of, the volcanologists, people who are actually going to study these, can now simply dig into a volcano and see, was this a certain type of rock? Was it oozy? Was it explosive? Was there layers of ash and tephra? Was there just volcanic magma? And you can kind of guess what a volcano was when it was active. Now that tephra is the erupted material, so it's the rocks, it's the dirt, it's the dust, it's the small particles, the larger particles built up in that magma, but not thought of as solid magma turning into a rock, but little pieces and puffs that stick out of it. So I just think of it as ash, but of different sizes. You can have dusty ash and then rocky ash, if you want to think of it that way. Now, when a volcano erupts, it's not just lava. The stuff coming out can be ash, it can be gases, it can be all this, and some of this will come rushing down the side of a volcano. And one of the things that kill people more than simply being, burned by the magma is pyroclastic flows, which are these essentially ash falling down the side of a mountain at very, very high speeds, along with all the gases that came out of the volcano at the time. In Martinique in the Caribbean in 1902, there was a serious volcanic eruption that destroyed an entire town, and it wasn't the lava that killed people. It was the gases and the tephra that basically covered a town in just a few minutes.